Alright, this video is the second part of the lesson dealing with standard deviation and variance and spread. So this is going to talk about how standard deviation, and we talked a little bit about this in the first part of the lesson. This is going to talk about how standard deviation deals with the spread of the data. And there's three methods, these three methods here that we're going to talk about that deal with just different ways that you can try to interpret some of the data or get how the data is spread out. These are just three different ways. The empirical rule is the one that we'll use throughout the year more than the other two, but the other two we will use a little bit here with this lesson. So the range rule of thumb, range rule for most data, it works for most data sets. The majority of the data lies within 2 standard deviations of the mean. Recall that the range is always the high minus the low. To estimate the range, this is if we already know the standard deviation. So if we already know the standard deviation, we can estimate the range by taking 4 times S, and then the alternative of that, or the reverse of that, is that the standard deviation is going to be about the range divided by 4. So we just take the range, high minus low, divide it by 4, and that's going to give us something pretty close as far as the standard deviation goes. It's not going to be exact. That's right, why it's called a rule of thumb, because we're sort of given a quick estimate. So that's just a way to quickly estimate what the standard deviation is of a set of data. Interpreting standard deviation using the empirical rule. The empirical rule is also called the 68, 95, 99.7 rule. And all that means that for data with a symmetric, remember symmetric is like the bell-shaped curve, so it's going to look like something like that, where it actually makes that bell. It's not skewed left or skewed right, so it's symmetric. The standard distribution has the following characteristics. This is what we were talking about when I was talking about your grades and how some college professors grade on the bell curve. About 68% of the data lie within 1 standard deviation. So if we're looking at a graph, and this is our mean, and we take the mean and we add whatever our standard deviation is, we add 1 standard deviation to it, and we talked a little bit about this last time, or we subtract 1 standard deviation, they're saying that 68% of the data should fall within that range. So a little more than 2/3 of the data should fall within that range within the mean. About 95% should lie within 2 standard deviations. I drew my thing in a bad spot here, but if we go out another standard deviation away from that, so if we take whatever number we came up with here and we add the standard deviation to it, we're saying that about 95% of all the data is going to fall within there. That's within 2 standard deviations. And then about 99.7 fall within 3. So if we go out to another standard deviation away from the mean on each side, 99.7%, or almost 100%. And it's not quite 100 because every now and then you're gonna have, some outlier that happens to fall outside of that. Not real often though. So that's the rule, 68% within one standard deviation on each side, 95% within two standard deviations, 99.7% within three standard deviations. We talked a little about this last time, in the fact that most of the data, or if the data falls outside of two standard deviations, then or any data that falls outside is unlikely outside of two, and any data that falls outside of three standard deviations is very unlikely, or very unusual. This is what the bell curve looks like. Instead of me drawing that last time, this is what, so we're saying 68% of the data falls in the blue right here, in this area, 68% of the data. Then from here to there is 95%, and then from here to there is 99.7%. And you can notice all you do is you take the mean and you add a standard deviation to go out that far. Then you take that number and you add another standard deviation. You take that number and add another one to get out to your third one there. Each time we go out 3 standard deviations away from the mean on the right and on the left. So this is just what we said. Each standard deviation on each side is about 34%. For the first standard deviation there, on each side it's about 34%. Then split it up. If we split it up and to get to 95%, we split these two in half and get 13.5 on each side. If we add these 4 up, we get to 95. And then the last two parts out here, the little aqua looking parts, are about, we usually, it says 2.35%. A lot of times we'll just say about 2.5%. So that's pretty close still. So that's what the empirical rule looks like. So if we're dealing with a set of data and they ask you how, let's say we have a set of data and it has 50 things in the set, 50 items in the set of data, and they say how many of those items are going to fall within one standard deviation of the mean, then we could just take the 234% here, which is 68%, and times that, so change it to a decimal, 0.68 times 50, and we just multiply those two, and that's going to tell us how many of these pieces, or how many of these 50 pieces of data fall in here somewhere. And we could do the same thing to figure out how many fall in this little part or this little part. You just take the percentage times the total number in the sample or in the population. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States ages 20 to 29 was 64.3 inches with a sample standard deviation of 2.62 inches. Estimate the percent of women whose heights are between 59.06 and 64 inches. If I'm looking at this, probably the first thing I start to do is I draw myself a little number line, and they tell us that United States the sample mean height was 64.3, so I put that 64.3 right there. That's gonna go in the middle, that's your mean. If you draw this out each time, it's gonna be real helpful to you. Then they tell us that the standard deviation is 2.62. Well, I know I'm gonna go 3 standard deviations that way, 3 standard deviations that way. And probably I'm gonna have to grab my calculator. All you're gonna do is this way, you're gonna add 2.62, then to that number, you're gonna add another 2.62, then another 2.62, and then going the other way, you're just gonna subtract off that 2.62. All right, so I went ahead and, again, on this side, I added on to the standard deviation, the 2.62, 3 times out through there, so this is 1 standard deviation, 2 standard deviations away from the mean, 3 standard deviations away from the mean. Then on the other side, I subtracted it, and you're 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. And remember, these are estimates, so we're estimating about how many women should fall in this certain range that they want here. Well, they want us to go from 59.6, which is right here, to 64.3, which is right here. That's the mean. So we're going from here to there. Well, 1 standard deviation below this part right here is supposed to be 34%. And if we go back, to here, you see that that's 34% right there. And then another standard deviation down below that is 13.5%. So this part right here would be 13.5%. They want the estimate of what percentage of the women fall within that range. Well, all we're going to do is take the 34 and add the 13.5, and we get 47.5%. So just a little below 50% of all women in America should fall within that height range, 59.06. And we could go around and ask the young ladies how tall they are and see if that, if that about fits it. Our class isn't really big enough to get a real good sample, but that's about what it should be, is about 47.5%. So here's just a little better drawing of it. Again, we're looking at this one and this one. That's where they wanted to go from this point to that point. That's what we were looking at. All the women fall in there. I'm not sure how to pronounce this guy's name. Just call him Chebyshev. So Chebyshev's theorem, the portion of any data set lying within K standard deviations, where K is greater than 1 of the mean is at least. This is the formula for Chebyshev's. Again, this is just an estimate of the amount of the data that falls within that variable K there. So we might go 1K, 2K, or K equals 2, or K equals 3, whatever, within that. So, and that K is supposed to stand for your standard deviation, sort of how many standard deviations you are. So if K equals 2 in a data set, at least, we do 1 minus 1 over 2 squared. Well, 1 over 2 squared is 1/4. And 1 minus 1/4 then is 3/4, or about 75%. So we're saying about 75% using Chebyshev's theorem. We're saying about 75% of all the data should fall within those 2 standard deviations, one either above or below the mean. with Chebyshev's, what's different is that his theorem works for any data set. And I shouldn't probably say any data set because it's not going to work for everything, but his theorem basically works for all. On the other stuff that we were doing, ignore that stray line going up through there, using the bell curve, the empirical rule only works for data that is basically symmetric. All right, it doesn't have to be exactly symmetric, but it has to sort of look like that bell curve, or if we're on a histogram, you know, it has to sort of look somewhat symmetric. So it has to have that shape to it. So the empirical rule works for stuff that sort of fits the bell curve, and Chebyshev's works for most any kind of data. So that's why we have that, and that's why within 2 standard deviations we're saying it's 75% instead of using the empirical rule, it was 95%. If we go out 3 standard deviations using Chebyshev's, and we're going to be able to say that probably about 88.9% or about 89% of the data falls within 3 standard deviations. So if we look at this example, the age distribution for Florida is shown in the histogram. Notice that the histogram is not symmetric. Apply Chebyshev's theorem to the data using k equals 2. So again, that k stands for how many standard deviations we're going. So we're saying we're finding the mean, whatever the mean is, wherever the mean is in this range here. So wherever the mean falls along through here, we're finding the mean, and then we're going 2 standard deviations this way and 2 standard deviations that way, and we want to know what percent of the data is going to fall within there, and then we'll also use that to find something else. So, and I didn't even see this, they tell us that the mean is 39.2, so the mean's going to be somewhere like right in here, in that range, somewhere in there, and we're going out 2 standard deviations each way. Well, if we use that, just like with what we had before, we do 1 minus 1 over k squared, but k this time is 2, so 2 squared. We just got done doing this, and that ends up being 3/4, which is 75%. So we're saying that 75% of the data should fall within those 2 standard deviations above and below that 39.2, which is our mean. Now, what we can conclude from that is we can actually get the age, since we know the standard deviation, which is right here, our sigma, which is the standard deviation. We can conclude that these that people that live in Florida, 75% of them are between one age and another age. And that's what I've done here. So we use k as 2. If we go from our mean, if we go out 2 standard deviations, both ways. If I'm looking at this and our mean is 39, just to draw my own up here, 39.2. If I add a 24.8 to there, add a 24.8 to there. So if I grab my calculator and let's see here, we got 39.2 plus our standard deviation, which is 24.8. That's 64 there. Add another 24.8, which would be 88.8. Going that way, we come down this way, and we subtract off 39.2 minus 24.8. We end up with 14.4. And then if we subtract off another 24.8, we end up at like negative 10.4. Well, you got to remember and use a little bit of common sense. We're dealing with age, so that can't happen. So we're actually going to stop at 0. Can't have somebody that's a negative 10.4. All right, so we're going to stop at 0, and that's what this is saying. So we're looking at the fact that if we do Chebyshevs, that 75% of the population of Florida fall between 0 and 88. And again, these are estimates. Some of you are probably saying, right off the bat that, well, no kidding. That's not hard to do, to say 75% falls between 0 and 90, because that's probably even a higher percentage than that. But that's using Chebyshev's theorem. And again, it works on any set of data. Notice that this isn't symmetric. It doesn't fit that bell curve. So it works for anything. Gives you a decent estimate. Not a great one, but a decent one. Standard deviation for grouped data. So standard deviation for group data. No, don't disappear on me. So standard deviation for group data, this is the formula. Sorry, I lost my box there. This is the formula that we use if we're doing group data. What I mean by group data is sometimes we'll have something and it'll say, okay, if we have our whatever our group is, we might have some that at 1, some at 2, some at 3, and there's 10 at 1, 7 at 2, 5 at 3, whatever. So it's some kind of data where the numbers are actually grouped and we don't have all the numbers just listed out. So we can use this formula to find standard deviation. Notice the only thing that's different in this formula is on that top part, you stuck in an F. So we're actually going out one step farther than what we did the other time. And you don't use this on every set of data, just if the data is grouped together like this right here. So that's the standard deviation. The variance, of course, would just be if you got rid of the square root there, that would give you the variance of the group data. Then to find standard deviation, we take that square root. When a frequency distribution has classes, estimate the sample mean and standard deviation by using the midpoint of the classes. So if we're doing one of our frequency distribution charts, and we have our classes here, then you're gonna, let's say the class goes from 0 to 4 or 0 to 5, then you just find that midpoint in there, and we use that to help us find the sample mean like we did in last section. So we find that sample mean, then we use that to come up with, or use this formula. So if we had this big set of data here, you collect a random sample of the number of children per household in a region, find the sample mean and the sample standard deviation of the data set. So we're going to do all that just using that big set of data. I went through and I found out if they had 0 kids, there was 10 of those. 1 kid was 19 families, 2 kids was 7 families, 3 was 7, 4 was 2, 5 was 1, 6 was 4. Then I took X times F, got all those numbers. So we did, down here it's telling us our frequency. We did 50, we researched 50 families. So that's our frequency distribution there. We find the mean. Our total over here was 91 when we added all those up. We divide that by how many of them we had, which was 50, and we get 1.8. So that's the mean. That tells us that average family has about 1.8 children. So we found that mean, that X bar. We make our chart here, so we got X, we got F, our frequency, then we take X minus X bar, we got all that down through here. Remember, if we add all those up, it should come up to 0. Then we square each one. Now we're going to add one more part to our box that we made last time, if we're doing this out longhand. And when we add that one more part, all we're going to do is we're going to take each of these numbers and we're going to times it by the frequency. So we're going to times it by that number right there. And that's going to give us these numbers. Now all we're going to do, and all this whole thing here just means we take all of those and we add them up. Once we add them all up, we get 145.4. So we're just adding another thing to our box. If you remember our box from last time, if we draw it, we got X there, that's each thing. We got here, we got our frequency. Then we got, sorry, I didn't make it big enough. We got X minus X bar in that one. Then we had X minus X bar squared. And now we're adding another box where we just take that number times the frequency. So we're adding another number to that box so that we can work this out. We use our formula. It says find the sample standard deviation. This is our formula. We just figured out that all this on top right here was that by doing our box on bottom, we got n minus 1. Well, n is 50, so we do 50 minus 1. If you're going to plug this into your calculator, then make sure you put parentheses around that 50 minus 1. And when it comes out, it gives you 1.7. Again, if you wanted to find the variance, you would just take that 1.7 and you would square it. So the standard deviation is about 1.7 children. That means if we took it, the mean was 1.8, and if we wanted to make our little curve here, which it's not gonna work out real well, because when we go down this way, if we subtract off 1.7, the standard deviation, we're at 0.1, and then we're negative children. So not very many people are gonna have negative children down this way. And if we add it here, that'd be 3.5, and then 5.2, and then 6.9. So that's sort of what it looked like. This is probably not going to, if we graph this, it's probably not going to be symmetric. It's not going to really fit the bell curve. Anytime you're dealing with standard deviation, anytime, it's a good idea to just draw something like this. Draw a little number line, put the mean right in the middle, and then 3 standard deviations up, 3 standard deviations below, just to help you understand what it is that you're actually dealing with. Coefficient of variation describes the standard deviation of the data set as a percent of the mean. You can use to compare 2 sets of data with different units. So we use this like this coefficient of variation. If you took a science test and a math test, we might use it to compare those two. To say, all right, who actually did, you know, if you scored right in the middle or close to the middle in both sets, did you actually do better on the science test or the math part? And that's what the coefficient of variation is. So if we have it, this is the formula that we're going to use if we have a population to find the coefficient of variance or a variation. Sigma, that's your standard deviation, divided by the mean, which is mu, times 100%. And that's just going to give you a number, a percentage that we're going to call the coefficient of variation. If we're doing a sample, then instead of sigma we use S, and instead of mu we use X bar. So those are the 2 formulas. You need those 2 formulas to be able to find the CV. Again, most of the time we'll be using samples, not populations. But sometimes they'll throw in that it's a population on the problem. You have to make that decision. Table shows population heights and weights in pounds of the members of a basketball team. Find the coefficient of variation for the heights and weights, then compare the results. So here we're comparing heights to weights, 2 different kinds of measurements. That's what we're going to do in this problem. So again, we're comparing heights to weights. So not the same thing, but we just want to see how they vary in relationship to each other. So if I do the CV, the coefficient variation for the heights, and this time we're using it as a population, so we're using sigma and mu because it's the whole basketball team and there's, you know, it's that whole population. The mean height was 72.8, so I'm just going to take, that's going to go on bottom, and then the standard deviation was 3.3. If we go back and look at this, what we can do is we can plug, so the heights, if we're doing the heights first, we can take all of this and plug it into our calculator, and that's what I did. So we take it all, we plug it into the calculator, and we find the mean and standard deviation. So I found the mean and the standard deviation, that's here and here. and then when we plug it in here, times it by 100%, we end up with about 4.5%. So that's our coefficient of variation. Sort of saying that it, varies about 4.5% from player to player as you're going through it. That's the heights. Now we do the same thing for the weights. If we go back to the chart and I plug in all the weights, I end up with the mean being 187.8 and the standard deviation being 17.7. So I'm going to do 17.7 divided by 187.8. That's going to give us our CV. I times that by 100% and I end up with about 9.4%. So from player to player, their weights vary about 9.4%. So what we can say, the other one was 4.5%, the heights. So the heights are closer to each other than the weights are, because the weights vary more. Because the weights vary by 9.4% and the heights only vary by 4.5%. So the weights are more variable than the heights. All right, so what we covered, the range of the data, high minus low, variance, standard deviation for population and sample. Remember, empirical rule is going to be very important throughout the year. We're going to use it a bunch. Chebyshev's theorem, we're not going to use it a whole lot, but we will use it a little bit. What we covered today, approximating sample standard deviation for group data, whether it's something with classes or something that's just grouped together. Be able to use the CV, find the CV, and understand how you can, say, okay, this one varies more than that one, what we just covered there. Just add this to the previous assignment.